Maddah from emotion, and actually we talk on Moser-based algorithm over univariate and bivariate differential fields.
Okay, thank you for the invitation and for the opportunity to present the ongoing work or a part of it in my thesis. So what I call Moser-based algorithms are the generalizations of the algorithms based on the reduction criteria given by Moser in the 1960 and the algorithm of Barkato given in 1995 within the study of linear ordinary differential systems with singularities. And as you have seen in ACA, that I'm interested within my thesis in constructing a fundamental matrix of formal solutions for two systems which can be seen as a generalization of the univariate linear differential system. And this is why I'm interested in the generalization of such an algorithms. So before going through my work, I'll start by giving them motivation why it is important or it is vital to generalize these algorithms to the bivariate fields and how they can be manipulated and used. And so I suppose that Ka is a commutative field of characteristic 0 equipped with a derivation delta. You see here is a field of constant. And V is an undimensional K vector space, and the matrix, and I'll take a matrix A whose entries lie in K and in K. And so this operator will be a delta differential operator acting on V, that is a C-linear endomorphism of V satisfying this Leibniz condition. And so at the beginning, I'm using the terminology of operators to unify the systems I'm working on, but later I'll be working directly on the matrices. So as an example of such an operators, if we take Y to be an unknown n-dimensional column vector, the trivial case, of course, will be if delta is a zero map, then we will just get the linear operator, and A epsilon here will be a perturbation of the constant matrix. And so we will be dealing with the eigenvalue eigenvector problem. Now, if we take delta to be the x d by dx, and we take K to be the field of formal meromorphic power series, then we will have this singular linear differential system. The systems I am interested in, the first one is the singularly perturbed linear differential system, and here K is, I'll take it to be the field of formal meromorphic power series in X and epsilon, where epsilon is a parameter, and I'll take the derivation of this form. And so we can rewrite the system in the form below. So this will be a work over a bivariate field. Another system I am interested in is the singular linear partial differential system in M variables, or the completely integrable Pfaffian system with normal crossings. And here we have M variables, so it is a multivariate field, and we have a set of operators, delta I, delta J, which compute pairwise. So in other words, we can rewrite the system as you can see in below. Now, to go back to the initial to the univariate case, I will explain on this univariate case how we can construct a fundamental matrix of solutions, but not to repeat myself with the things I've already said in the conference. I'll show that within an example and to save time on that. So again, this is the singular linear differential system. And
so, excuse me, do you assume that the exponent P is positive? I mean, minus P, so P is positive?
Yes, here I suppose that P is positive, and the reason, within the formal reduction, I'll talk more about that. But here you can see in the presentation before, If P is equal to 0, then we have a regular singular system. If P is less than 0 strictly, then we have a regular system without poles. And if P is greater than 0, then we have an irregular singular system. And this will be the more interesting case. And now we will see within the solution how will be this illustrated. And so this kind of systems, it is well known. This is a result by Turretin since 1955 and then by Levelt in 75, that these systems have a normal form which can be explicitly prescribed, and it is very close to the Jordan decomposition of linear operators. And so in this linear form, we can always find a change of bases such that under additional ramification, this change of bases will result in a matrix presentation, A tilde, where A tilde is a diagonal block matrix, and each A tilde I is a sum of a nilpotent matrix and a diagonal matrix. Now these WKs will be called the exponential parts. Well, these are properties, and NK, as I said, is a nilpotent matrix in upper triangular form. Now, what we are interested in is that this canonical form allows us to write the solution in this manner. And so here you can see that the Q is can be obtained by formally integrating the WKs which appeared lately. However, although we know this normal form and we know the form of the solution, the question of the construction of a fundamental matrix of solution is a question of another nature. So, what I mean by formal reduction, it is the algorithmic procedure that computes the transformation, this change of bases, and these ramifications S, the changes in the independent variable, which take the system into its triangular form so that formal solutions can be constructed. And the idea is that at every step we find a transformation T such that the new resulting system either has a smaller dimension or a smaller Poincaré rank P.
And,
yes.
So you assume that A is computable.
A?
So what do you mean you construct? Because your original is a series.
Yes, yes.
So AK are computable.
Yes, and in fact, there is a result that to obtain the exponential part in the solution, we need a certain number of the coefficients in AK. We do not need the whole coefficients.
Okay,
and in particular, we need the first n times p coefficients. And then to find, and then for the regular part, or the part of phi x lambda, we can truncate as much as we want. So this problem had been studied extensively, and algorithms for related problems, which will lead eventually to the construction of a fundamental matrix of solutions, have been given by various authors, including Lovell, Hilali, Wesner, Sommerling, Shin, Barcato, and Fugel. The existent results, the results of existence, as I said, date back to Turretin and Lovell, also to Balser, Lotz, and there are the well-known books of Vazov, Balser, Siguia on this kind of equations. And these algorithms led to the package Isolt, which is written in Maple by Barcato and Fugel, and which is based on this Moser-Barcato algorithm, which I will explain now. And it is dedicated to the construction or the formal reduction of such systems. So how is that done? Now, the idea, as we said, is to find at every step a transformation which will lead to a system either with a lower dimension or with a lower Poincaré rank. And usually the discussion is according to the eigenvalues of A0. So we will have three cases. Here, the assumption that P is greater or equal to 0, as I said, is just to deal with a more difficult case, that we have a singular system. Otherwise, it will be a regular system. Okay, so what is the effect of a change of basis? As also we have seen, if we have an invertible matrix T, then this Lowy change of basis will, or linear transformation, will result in an equivalent system such that A tilde and A are related as you can see. And here we can see that the difference from the linear operators is that we have this differential term which we have to pay attention to, in addition to the similarity term T minus 1 AT. So I'll follow here the reduction, recursive reduction, which is given in the paper of Barcato in 1997. And the first case would be that A0 has at least 2 distinct eigenvalues. In this case, we can uncouple the system into systems of lower dimensions via the classical lemma. A constructive proof can be found here, although it dates back to the 30s. And the theorem states that given this system, if A0 can be written in the following block diagonal form such that A01 and A02 have no eigenvalues in common, then there exists a unique transformation, which you can see is invertible in the ring, such that, or it is unimodular, such that the change of basis will result in a system which is uncoupled as follows. And now we can deal only with the system whose matrix is A1 tilde and the other system whose matrix is A tilde 2. And now we can assume without loss of generality that A0 has a unique eigenvalue gamma. And in this case, we can apply the so-called eigenvalue shifting. The only effect of this shifting is that it shifts the leading coefficient matrix A0 by gamma I, and so now the new leading coefficient matrix of the resulting system is nilpotent. This is the most interesting case, and if A0 is nilpotent, then there are 2 steps. In the first step, we try to minimize the Poincaré rank P and the rank of the leading matrix A0. And here is where we use this reduction algorithm. Now, if after this step, the leading matrix A0 is still nilpotent, then we will have to compute the so-called Katz invariant, and we will need to introduce ramification in the independent variable. I will not talk a lot about this step because I'm interested in the first, but I illustrate by an example. So given here AX, here you can see that the Poincaré rank is 7, and we can compute this transformation by Moser-Barcato algorithm, which will result in an equivalent system of this form, and here you can see that the new Poincaré rank is 2. And this is actually the true Poincaré rank computed. So it is the minimal rank that we can obtain by any change of basis. So it might happen that at this point the leading coefficient matrix might have distinct eigenvalues, and so we can apply again the splitting lemma. If not, we proceed to compute the Katz invariant. So the Katz invariant can be seen as the order of the polynomial in x minus 1 in the exponential part, which is in the solution. So in this example, it is 5/3. This means that if we take the ramification x equal t cube and apply again Moser-Barcato reduction algorithm to get to the lowest Poincaré rank, the true Poincaré rank should be 5. And the resulting system has 3 non-zero distinct roots. At this point, we can apply again the splitting lemma, and so we can proceed in this recursive algorithm. And so, as I said, as I'm interested in the generalization of this algorithm to the bivariate fields, in the first part, I will recall the Moser-based algorithm. In the second part, I will talk about its generalization to the singularly perturbed linear differential system. And then in the third, to the singular linear partial differential system in two variables. Now, if I had time, I will talk about how can this algorithm be used as well in the algebraic case, in particular in the algebraic eigenvalue eigenvector problem, which I'm interested in as well because it is important to compute the Katz invariant. So again, these are the notations of the system over the univariate field. And again, this is a fundamental matrix of formal solutions. Now, if a Q is not a null matrix, then the origin is called an irregular singular point. And in this case, the elements of a Q determine the main asymptotic behavior of the actual solutions as x tends to 0 in sectors of sufficiently small angular opening. And in this case, P cannot be reduced to 0. Otherwise, the origin is called a regular singular point of the system. In this case, S will be equal to 1, so we'll have no ramification. And the formal series phi converges whenever the series of AX does. But we do not know from the outset whether Q is null or not, so we do not know if the system is irregular or not. And this was the motivation of Moser to give this criteria to distinguish regular systems from irregular systems. Moser defined two rational numbers, the Moser rank MA, which is the sum of the Poincaré rank plus the rank of the leading matrix A0 over N, and the mu A, which is an invariant of the system. It is the lowest Moser rank that can be obtained upon any change of basis. And he gave this criteria that if MA is greater than mu A, or MA is greater than mu A if and only if this polynomial theta vanishes identically in lambda. And as you can see, this polynomial depends only on A0 and A1. So we can know from the outset whether we can still reduce the rank of the leading matrix A0 or the Poincaré rank. And so in the case that theta lambda is equal to 0, the system and respectively AX is said to be Moser reducible, and MA can still be diminished by a change of basis. Otherwise, it is said to be Moser irreducible. So this is the example I showed before. Here for AX, if we compute MA, it will be the Poincaré rank P plus rank of A0 over the dimension 4. However, we do not know if it is the minimal or not. So if we compute theta, the polynomial, theta is equal to 0, so we can still minimize either the Poincaré rank or the rank of the leading matrix A0. And this transformation will do this work for us. So for the resulting system, A tilde, if we compute now the polynomial theta, it will be non-zero. And so M of A tilde is equal to the Moser invariant of the system, which is 5 over 2. Now,
when the two are equal, is that the minimum?
Yes, when the two are equal, it is the minimum. However, we do not compute mu A. We know that if theta is not equal to 0, then mu A is equal to MA. What we can compute is MA, not mu A. And we use this theta criteria to know if they are equal or not. And another thing is that the reduction happens at the steps. So it might be that theta is equal to 0, but the rank of A0 can be reduced, but not the Poincaré rank. Because we reduce the rank of A0 at each step till the Poincaré rank drop. And we repeat again. So here's the description of the algorithm given by Barcato in 1995. Here's the system again, and without loss of generality, we can assume that A0 has this form where A011 is of dimension R, which is the rank of the matrix, and A011, A021 is a n by r matrix of full column rank R. And of course, we can always obtain this form by a constant transformation. Now, in the second step, he proved that the determinant of, he constructed this matrix pencil where we take the first r columns from A0 and the last n minus r columns from A1, and we add lambda I and minus r. So he proved that the determinant of this matrix pencil is equal to 0 if and only if the polynomial theta vanishes identically in 0. And this matrix pencil will be important because we depend on it to construct the transformation, as you will see. So if theta is equal to 0, this means that G lambda A is singular. And it means in particular that G lambda equal to 0A is singular. That is, if we substitute lambda equal to 0 in G lambda, it is singular. Or else we will not have theta equal to 0. So if we let E be the vector space spanned by the first r rows of a G lambda equal to 0A, and if we let F be the vector space spanned by the last n minus r rows, then we can discuss depending on the linear dependency relations between the rows of E and F, or the basis of E and F. Now, if dimension of E is less than the rank, we set row equal to 0. Now, this is very technical, but soon I'll show an example. Otherwise, if the dimension of E is equal to R, this means that there are some dependency relations between the rows in F. And so we can find the row always such that, in this case, we'll compute the left null space of G lambda 0, and we can always find a vector who will have at least one non-zero element within its R plus 1 and nth entry. And we can always suppose that the Wn in this vector is equal to 1, or else we can perform a permutation. So here, basically, it is some Gaussian elimination and some permutation matrices, transformations. So now, if we take a matrix R1, whose nth row is this W1, and whose other rows are just coming from the identity matrix In, and we apply it to the matrix A, we will get a new matrix or a new equivalent system whose matrix I denoted here by A1. Now, this R minus 1, 1A, this form between braces only to denote this linear transformation. If the upper left n minus 1 block is still singular, then we repeat the procedure again and we increase row. Okay, so at the first we had G lambda in the form A011, and well, we had here U1, U2, W1, W2, M2, W3 were coming from A1, and the first R columns were coming from A0. And as we increase row, we get this form. Now, the point of this form is that now we have M1 and M2 depending, or linearly depending on A011 and U1. So if we perform a shearing transformation, or a polynomial transformation, the columns of A0, in particular V1, will be multiplied by X. And in A1, these columns, we have U1 and M2 will be shifted by X minus 1, so now they will be in A0, while W2 will be shifted to A2. So the new leading coefficient matrix is A tilde 0 of this form, and it has a rank less than the rank of the initial matrix. So again, we repeat this procedure. As long as the theta polynomial is equal to 0, we repeat this procedure to reduce the rank of A0. And as soon as the rank drops to 0, this means that the Poincaré rank is dropped, and we start all over again. Now, this irrational version of this algorithm, that is a version which aids in computing the rational solutions of such systems, is the one I'm trying to generalize here, is given in 95. However, other versions or newer versions of this algorithm are given by Baccato and Flugel in 2007-2009. Now, another work another work related more to the algebraic problems is the work of Junro and Flugel, where they borrowed this criteria of Moser to tackle the algebraic eigenvalue-eigenvector problem. And as you have seen in the seminar of Baccato, that they generalized this Moser criteria and the algorithm to regular systems of linear functional equations and applications, and gave its applications. As I said, what I'm interested in this talk is a generalization in another direction. It is the generalization to singularly perturbed linear differential systems and to a class of linear partial differential equations, or systems of equations. So the first problem, the singularly perturbed linear differential system. Again, here are the notations. And here, since we have we have a variable and a parameter, we will ask first if we have to work with respect to epsilon or try to diminish h, or we have to try to diminish p. Now, this problem also has, its study encompasses a vast body of literature, and it is traced back to 1817 with works of Iwano, Shibuya, Moser, Shin, Vazov, Makuta, and others. And, yeah.
So AK of x belongs to?
Yes, here AK of x has its entries in the formal meromorphic power series. So X may contain poles. And the basic motivation of working with such kind of system which contains poles in X but not an essential singularity is that the transformations we perform to construct a formal fundamental matrix of solution might introduce poles in X or elevate the order in X. And this is inevitable, and this is the way it is done with in the case of equations. So this is the motivation to work with AKX having its elements or its entries as meromorphic power series in X, not Taylor series.
Then what is the point of x to the negative p?
Yes. Yes. This is a factorization for A0. So here A0x is doesn't include the poles, while the others might include poles. So here only A0x does not include poles. Okay, so here if we try to generalize the formal reduction in general and the Moser algorithm in particular, the first obstacle is that here A0x is not a constant matrix and we have to deal with a matrix function. So in the particular case, if A00 has at least two distinct eigenvalues, the splitting lemma still holds. However, it might happen that A00 is nilpotent, but A0x is not. And so in this case...
What's A00? Oh, X0.
Yes.
X0. Okay.
So it is the constant leading matrix. Now, here's an example of a turning point, or what we call a turning point. Here, I'm expanding the system with respect to epsilon. And here, you can see that A0x has this form. A0x has two eigenvalues, 0 and x, while A00 is nilpotent. And so here, we cannot just proceed directly. We have first to try to eliminate the turning points. And in addition to the difficulty of turning points, we have to do the computations over bivariate fields. There is a correlation between the poles. We have to pay attention when we are trying to diminish h if p will increase and vice versa. There is also the problem of deciding, as I said, whether to diminish h or diminish p. And the most difficult problem is still the analytic justification of the kind of formal solutions that we get in the end of formal reduction. Now, till now, there exist no implementations for computing the solutions of such system, and the approaches are the semi-classical approaches which existed since the 70s for the linear ordinary differential systems over the univariate field, that is the non-perturbed systems. And while the study of the non-perturbed systems or witnessed a profound advancement in the last 2 decades, these perturbed systems did not witness the same development. And this is our main motivation to try to generalize the techniques that we use for the non-perturbed systems for the perturbed ones. And this was the hope of Vazov in his 1985 treatise summing up the research results on such systems. Now, to try to generalize the Moser-based algorithm, we have to proceed, as we have seen, in 2 steps. The first is the resolution of turning points, and then we have to perform the reduction. Now, in this case, for these systems, we choose to diminish diminish h to its minimal integer value and not x, because in case h is equal to -1, then in this case we can write the solution y as an expansion in in epsilon, not power series, and then we can substitute this expansion into the system, and then we can reduce the problem to solving non-perturbed univariate systems which are non-homogeneous. So in this case, we know how to solve the system. And this is why it is more plausible to think about diminishing h and not p. And this is why I expand the system in epsilon and not in x. So to reformulate the definition of the turning point, A0x is said to have a turning point at x equal to 0 if in any neighborhood the Jordan form is unstable.
And this unstable means what?
Yeah, it means that either the multiplicity of the eigenvalues is changed or the dimension of the Jordan box, as we have seen in the example. So our theorem states that suppose that A00 is a nilpotent constant matrix. If A0x has a non-zero eigenvalue, then we can find a positive integer s and a transformation such that by setting x equal ts and taking the change of basis, the leading matrix of the equivalent system is such that the new constant matrix has at least 1 zero constant eigenvalue. So we go back to the splitting lemma. And in the proof, first we remark that a change of basis will have this effect on the system. A tilde, the matrix of the equivalent system, and A are related as follows. And if we are interested only in A0x, then it suffices to look at this relation. So we are not interested in the differential part. It is enough to study the similarity part in this relation. And it is known that the eigenvalues of A0x, we already suppose that there exists at least one non-zero eigenvalue. It is known that the eigenvalues can be expanded in fractional power of x or Puiseux series in a neighborhood of x equal to 0. We are only interested here in the leading exponent of such series. So we take these eigenvalues, we expand them, and we look for the minimal leading exponent among them. And it is known, of course, that we can compute these eigenvalues by, well, there exist at least 3 approaches I am aware of, but one of them is simply to compute the characteristic polynomial of A0x, so it is a scalar algebraic equation, and it can be solved by a Newton-Puiseux algorithm. We are interested only in the first term, non-zero term. So we take the minimal leading exponent, and we set x equal to ts, where s is the denominator and the minimal leading exponent among all the other eigenvalues. So for now, we can assume that S equal 1, otherwise we can take this ramification. At this point, we can apply Moser-based reduction to A0x, so it is Moser reduction in X and not in epsilon at this point. And this can be done by the algorithm of Barcato and Flugel in 2009. After applying it, we will be sure that there exist n minus degree theta eigenvalues having leading exponents in 0, 1. And this is a way to see that that this polynomial theta includes information about the system. It is not. If it is not equal to 0, then it is still interesting because it gives information about these leading exponents. Now, since the leading exponents lie between 0 and 1, and we already assumed that S equal to 1, then necessarily mu 0 is an eigenvalue of A tilde 0, 0, and it is non-zero. So this is how we can treat the turning points. Now, this is the first part, and here we applied Moser-based reduction over, we applied it for A0 tilde X. However, we will see later that we will apply another Moser-based reduction for epsilon to reduce the rank H in epsilon. Now, this is an example, the same example I showed for the turning point. The statement of this example is from Vazov, but the method is using our algorithm. Here, we can see that the eigenvalues, again, are 0 and X. And so S here is equal to 1 because the only eigenvalue is X. And the transformation we can compute is this transformation, which will lead us to this system. Here you can see that the new A0X has two distinct eigenvalues, 0 and 1. So we can apply the splitting lemma and proceed. Now that we solved the problem of turning points, we can assume without loss of generality that A0x is nilpotent. And now we can think about diminishing H. And as I said, it is plausible to think about diminishing H rather than P. So we will define the Moser epsilon invariant and the Moser epsilon rank in this way by taking H and not P. Although the main motive of Moser for this criteria was for reducing the Poincaré rank P. And in analogous to the non-perturbed system, we give this definition. We say that the system is called epsilon reducible in the sense of Moser, or epsilon reducible in short, if m epsilon is greater than mu epsilon, and otherwise we say it is epsilon irreducible. And our theorem, which is analogous to the univariate case, states that given the following system, a necessary and sufficient condition for the system to be epsilon reducible, that is the existence of transformation such that the rank of the leading or of the new leading matrix is less than the rank of the initial one, is that the polynomial, this polynomial theta, vanishes identically in lambda. And here we can always choose Tx epsilon to be a product of unimodular transformations, which will not create new poles in X or elevate their order, and polynomial transformations of this diagonal form, such that alpha 1, alpha n are non-negative integers. Now for the proof, I will follow with an example. However, there is the direction. I will show one direction, and I will not show the other because the other is pretty much long, and I'm interested here in the construction. So I'll show only one direction. Now, given this system, here A0x is nilpotent of rank 2, so we construct in the same manner G lambda. We take the first two columns from A0 and we take the last two columns from A1. And theoretically, we need to use the Smith form in the proof. However, since we have here a principal ideal domain, we can, well, theoretically we can use it, but practically it is sufficient to use Gaussian elimination or to perform Gaussian elimination on the columns of A0x by taking as pivots the elements of minimum order or valuation in X. Because in the univariate case, we were using constant transformations in the Gaussian elimination, and here not to create pole, we can just use pivots of minimum order. So this is one difference. Another difference is that it may happen that the vector that we choose from the left null space might have entries like this example. W1 is X, and we have in the first position X, and in the last position X squared. So we cannot suppose in this case that the nth entry is 1. So we might end up with a non-unimodular transformation. However, by a simple trick, we can just take the first R entries to be 0 and keep the other entries, and the method can still work. So as you can see here that this is our, if we take lambda equal to 0 in G, and if we only permute, we will get this matrix, and here you can see that now we have, there is something, no, it is correct. Now these blue elements will be shifted from A1 to A0, and the red elements will be shifted from A0 to A1. And so in this case, by applying this shearing, we have this shifting, and we can arrive at the same result that we have obtained in the non-perturbed case. As I said, for the necessity of the theorem, I omit the proof. Now, here is a complete example, or an already done example. Given this system, here h is equal to 3. By this transformation, we can diminish h to 1. Okay, so now that we have this algorithm for the bivariate field, we might ask if it can be just simply adapted to the to other systems over bivariate fields, and for example for the singular linear partial differential systems in 2 variables. So again, here's the notations of the new system. Here I will only talk about the system in 2 variables. So a formal fundamental matrix of solution has this form, and they have been studied in the 70s and 80s by Charrière, Denis, Gerard, Leval, Sibuya, Van den Essen, and others. The algorithms for related problems of such systems, we have a rank reduction algorithm and construction of the solutions of regular systems is given by Kato and Leroux in his thesis. The closed form solutions of integrable connections were discussed also in a paper of 2012. And what we are interested in is to find the true Poincaré rank. We say that for these systems, the minimal rank P tilde Q tilde, such that P tilde and Q tilde are simultaneously and individually the smallest possible, we will call it the true Poincaré rank of the system. Now, as I showed in the conference, that a corollary of the theorem I showed there, that the true Poincaré rank of the system of this system of PDEs is P tilde Q tilde, where P tilde and Q tilde are the two Poincaré ranks of the associated system of ODEs. So the associated system is obtained by taking y equal or setting y equal to 0 in the first system and x equal to 0 in the second. We will have systems of ordinary differential equations, and the Poincaré rank of each of these systems will give us information about the true Poincaré rank of the system of partial differential equations. So here we can have a criteria. However, the difficulty or the reason that we cannot just apply simply the algorithm we have for perturbed systems is that for such systems, any application of a linear transformation on one of the subsystems will affect the others. And this is the example I've shown in ACA, that if we take this system and we apply this linear transformation, which can reduce the Poincare rank in X, it is true that we will get the Poincare rank will be reduced by 3 in X. However, the normal crossing is altered in this case because now we have poles in Y for the first system, and the Poincare rank in Y is increased by 1. However, we can still obtain a theorem which is analogous to the perturbed systems, and this can be done by studying the relations between by taking benefit of this commutativity, pairwise commutativity of the operators. So now if we perform this transformation, we can get a system which is reduced in both X and Y. And as I mentioned, that this will require additional structure on A0, so instead of performing Gaussian elimination only for to get the n minus r 0 columns, we have also to perform Gaussian elimination to get these 0 elements. And then by studying the integrability conditions, we can make sure that the entries in B tilde which are altered by x minus 1 divided by x minus 1 are already 0. Now, it is natural in this case to ask that several algorithms exist for the rank reduction in the univariate case or for the non-perturbed system. So why do we choose this algorithm in particular to generalize? Leroux, in his thesis published in 2006, he showed that the complexity of both Moser-based algorithm and Level's algorithm, which is given in 91, they have the same complexity. However, with an experimental study, we have observed that the coefficients in the matrix A grow dramatically with the algorithm of Level. So this is an example. Other examples exist on my website. Here, I give an example for the singularly perturbed systems. Here, A is Moser reducible in epsilon. If you compute the theta, we can know that it is Moser reducible. And if you compute the Moser rank, it will be H plus 3 over 6, whatever is H. I already know the Moser invariant, epsilon invariant, so I just put it to see that it is sufficient to run only one reduction step to drop the rank of leading matrix. So now I will show the effect of running only one reduction step. If we use the generalization of Moser-based algorithm, this is the transformation T, and this is the resulting, the matrix of the resulting equivalent system. However, if you use an adaptation of Level-Bakato-Lewis algorithm, I call it this way because it is a generalization of Level's algorithm to the Pfaffian systems given by Leroux and Bakato in 2006. We will get very complicated coefficients. Here I show only one entry from T and one entry from A because there is no space. So one of the criteria we considered that the reduction criteria in Level's algorithm is not strong, and so the algorithm might be running and running, although there is no need to perform more operations. So we adjoined Moser's criteria, which is the polynomial theta, to this algorithm. And the computations are reduced, but are still non-satisfactory, or at least non-satisfactory compared to Moser-Bakato algorithm. And this comes from the fact that in Moser-Bakato algorithm, at each reduction step, we know that we will reduce the rank by 1, at least by 1. However, in Löwel's algorithm, a reduction step does not necessarily reduce the rank. So I still have more time to proceed to the third part, or? Okay. So the third problem I am interested in is what information can Moser criteria and Moser-Barkato algorithm give about the algebraic eigenvalue-eigenvector problem. And the reason I am interested in this problem is that is that we needed to compute the Katz invariant. So I show this example again, and I said that the Katz invariant is the order in the exponential polynomial matrices in the solution. So it is 5/3 for this example, and we do not know it from the outset. However, in the result by Barkato in 1997 states that, now I go back to the univariate case, states that given this system, if we find the characteristic polynomial of a of x, then under certain conditions, the Katz invariant can be found from these coefficients, or the evaluation of the coefficients in the characteristic polynomial of a. And these coefficients can always be satisfied, these conditions. So the Katz invariant is or finding the Katz invariant tantamounts now to finding the minimal leading exponent within the eigenvalues of a of x. So the problem is reduced to tackling the problem of finding the leading exponent within the eigenvalues of a of x. So one approach to find these eigenvalues is calculating the characteristic polynomial and then running Newton-Puiseux algorithm. Another well-known approach, which acts directly on the matrix without reducing it to this, without computing the characteristic polynomial, is the well-known approach of Litsky, Vyshik, Lusternik. And in this approach, they consider the perturbation. Here, I consider the perturbation by x. And without loss of generality, we can assume A0 to be in the Jordan canonical form, J, and I will denote A1 by B. So here I will use Arnold's compact notation to denote the blocks of J. So here we have R1 blocks of dimension N1, etc., till we reach RQ blocks of dimension NQ. And we can, without loss of generality, assume that the dimension N1 is greater than NQ. So the cyclic characteristics of J, as it is known, can be represented as a partition of N. So sigma J will be N1 counted R1 times, etc., and NQ counted RQ times. So for this Jordan canonical form, for these Jordan canonical forms, we can give the cyclic characteristics are given by this notation. So in Litsky theory, what is done is that Litsky submatrices are defined. I'll define them with this example so that we do not use too many notations. So we block diagonalize B, which is the second term in AX, according to the blocking of J, the Jordan canonical form. So we had 2 blocks of dimension 3 each, then 3 blocks of dimension 2 each, and 1 block for this example. So we block B in the following form, and then we define the Litsky submatrices to be L1 will be the hearts, L2 will be the hearts and the spades, and then L3 will be in the following form. So they are, we define them from the elements in the left corner in each block. And then the determinants of these Li, Litsky matrices, will determine whether the matrix is a Litsky perturbation or not. If all these determinants does not equal to 0, then the eigenvalue splitting of A of x can be identified with its leading Jordan structure. So if we have here 2 blocks of dimension 3, then we have eigenvalues of order 1/3, etc. And in general, a generic perturbation of a matrix is a Litsky matrix. However, non-generic cases can still occur, as we can see in this example. If we set all the elements to be equal to 0 except the elements in red, if we set them equal to 1, then we can see that the first and the second Litsky matrices are equal to 0, while the third is not equal to 0. And so it is not a Litsky matrix. And the eigenvalues cannot be, the splitting of the eigenvalues cannot be identified with the Jordan blocks. So in 2000, Junho used the rightward coin move in the Furrer diagram to characterize the cyclic characteristics, because characterizing them this way allows us to compare 2 Jordan canonical forms. So for each element and the cyclic characteristic can be represented by a stack of coins. So for the first sigma, we have 3 coins, then 3, then 2, 2, 2, 1. And we say, we call a right coin move any move which can be performed without altering the monotonicity in these Furrer diagrams. So why I'm talking about this? Because here in the 2 articles of Junho, Flugel, and Junho, they borrowed Moser's criteria and algorithms of Moser reduction to show that if we minimize the rank J, the rank of a J over the orbit of A, which consists of all the similarity transformations we can perform on A, and then we minimize these cyclic characteristics over this subset of similar matrices to A, which have a minimal rank, and this can be obtained by elementary transformations and polynomial transformations, as in the differential case, then we can solve some singular cases in Litsky's theory. However, in the work of Junho, a singular case is still left, which is the case when we have, for example, for this example, we can see that A1, or upon computation, you can find that A1 has a minimal cyclic characteristics. However, it's still the splitting of the eigenvalues cannot be identified with the Jordan, the dimensions of the Jordan blocks. And if you compute the eigenvalues of A1, we can find that they are the fifth roots of X. However, A1 is not a Litsky matrix, as I said, although it has a minimal sigma. And to solve this, or another approach to solve the singular cases in the Litsky theory comes from tropical algebra, and we were trying to see whether these both approaches superpose. So, for the tropical algebra, we consider the tropical semi-ring, where the addition is the minimum and the multiplication is the addition in the usual sense. The purpose of such an algebra, or in such an algebra, we can represent a matrix by its valuation. And then we can study the graphs we can represent a matrix by its valuation, and then the valuation by a graph, and then study the circuits in this graph to find information, to retrieve information about the eigenvalues of the matrix. So without going through all these informations, I will switch to a theorem by Ekian, Babat, and Kuber in 2006, which states that in the non-degenerate case, if we represent a matrix A by its valuation, then the valuations of the eigenvalues of A of X can be found by finding the tropical eigenvalues of M. So in our case, since we are looking for the Katz invariant